a lab, so here they are, a little bit late, but I have them. And for number 1, you do the Bode plot for the high pass filter. Number 2, Bode plot for the low pass filter. Then number 3, we're going to compare the low pass and the two-stage low pass on the same graph. We're going to overlay them. And then for number 4, we're going to look at a plot of V out over V in for a bandpass versus omega for a bandpass filter. We're going to estimate the inductance of the coil using the peak gain frequency. So here's for number 1, you see the Bode plot for the high pass filter, and here this is the overlay. You can see that the cascaded low pass filter is clearly sharper and filters out more of the high frequencies more quickly. The bandpass filter is right here, and you can see that the peak frequency, we read it right off the graph. We read the supply voltage right off of our table, and we can use this expression to solve for inductance, but I found it very challenging, so I put it in this form for Wolfram, and I solved for inductance, and they told me it was 11.302 microhenries. Here's the Bode plot for number 2, by the way, for that low-pass filter. Assignment 21, we're plotting load lines over an IV curve for supply voltages of 0.5 volts, 0.6 volts, and 1.2 volts. We read these right off the graph, the y-coordinate of the intersection, and we get these currents, and here I show you the 1.2 volt supply voltage, and you can see the intersection here and the point. For number 2, you can see that I tried to solve this mathematically first before going for the graphical method, because I noticed there were 2 very nice expressions for current, so I solved for VD and multiplied this by current and in terms of VD, so it was pretty simple, and I got 0.0022 watts, and then I tried to go for it graphically because I wasn't quite sure how great of an answer that was, and I got a very similar answer of 2.5 milliwatts, so graphically you can see here for supply voltage of 1.5 volts, I continue this method, I multiply the coordinates of the intersection, and I do it again for negative 1.5 volts, even though it doesn't say it, and I get a very similar 2.5 milliwatts. Graphically, quadrant 4 has the elbow of the curve. The curve lies in quadrant 1 and 3 as well, but those both yield positive power. The load line intersects the IV curve in quadrant 3 when the supply voltage is negative 0.88 volts to 0.6 volts. And here you can see I showed the limits here on the graph with these 2 lines just for visualization. In assignment 19, number 3, I made a bad math error and some inaccurate explanations. After revising a simple trivial math error, I put 12 there instead. Now I have the correct capacitance, 20 microfarads. And for part B, they give you a recipe in the book for this peak voltage, and what we're trying to do is get the resistor at least 12 volts, which is the last thing in the circuit. It's going to have to drop across the diodes, and there's going to be a voltage ripple, and it only goes through 2 diodes, even though there's 4 in the circuit, because it can't travel in reverse through those diodes. The rectifier diode is 0.7 volts, and when I do out this kind of loop rule based thing, I get that the V peak must be greater than 14.6 volts in order to have a DC voltage rectified of 12 volts. So according to the relationship, we would get a larger ripple by replacing the load with the lower resistance, and we could compensate for this by making the capacitor bigger. This is true. For assignment 24, number 2, the AND gate, and number 3, the NOT gate, I have them on the same page next. It's taken me a few tries, but I think I have it here. Due to the loop rule, when A or B is 0, all of the voltage will drop across the resistor except 0.6 volts for the diode or diodes, and the output will be logic 0 because 1.2 volts is the greatest output we can get here, and that's less than 2.5. When A and B are 1, there will be less than 2.5, greater than 2.5 volts at the output, which is logic 1. When A is logic 1 for the NOT gate, we have here this NOT gate, and when A is logic 1, current will go to ground because of this voltage difference between here, and voltage will drop across resistor on branch A, and we'll get, an output of 0. But when A is logic 0, no current will flow through branch A. Therefore, no voltage will drop across that resistor, and F will be 5 volts, logic 1. For question number 3, assignment number 26, you could see here I did the wrong problem or something like that, and here I work it out again. It's a voltage divider question, and it's it's pretty cool, and we get this expression here for V plus with the voltage divider in terms of V plus and V in. We know V plus equals V minus, so we're going to get an expression for V minus now, and using the fact that I3 equals I4, we can set these two things equal to each other, and we know R3, we know R4. We can use the fact that I3 equals VR over R3, and I4 equals V4 over R4, which gives us these expressions in terms of V minus and V out, and we can set these equal to each other to get an expression for V minus. And you can see here that we get an expression for V minus that is 1/3 V out. And when you set this equal to V plus, you find that V out is 2 times V in. For number 4, this derivation question where we do it ourselves, you could see I restarted here. I never really started to begin with, but I state these facts, and then I go on to show you the current relationship using these facts that I have up here, and these will cancel out and reveal that V out equals, JV in R omega over R omega C, I think. I'm sorry I photocopied this so bad. Just look at the physical copy, and the verification is right below where I set it equal to, these expressions here that we are trying to compare them to see if we get logical results. And this proves the fact that we could set these equal to each other and get true statements, proves that the derivation does follow those two expressions from above. And our result is much more general because without that integral with respect to t, we're not specifying exactly what we want the voltage over in this in these expressions with the integrals. You get the integral over the voltage with respect to time, and that's more specific than generally without time. For assignment number 27, I have this quiz, and this quiz I did not do very well. Oh, here it is. I wanted to actually say that suppose we classify the outputs below as high or low, circle the ones that will go high. Well, this is simple because when we put a higher voltage into V plus, all the voltage is going to shoot up to that 5 volts, and as opposed to going, if it were to go into the inverting input, where it would shoot all that voltage down to the ground. So we would need to get the higher voltage in the non-inverting input in order to get a high output. And one more for assignment 8. I have been messing up the flip-flop thing, and now that I have done this project, I'm really getting it now, and I've redone this truth table out for the flip-flop and what happens. And if you notice, for the 1-1 state, it's non-changing. It will never change the previous output. And that is a good way of describing the 1-1 input of the flip-flop gate. Thank you.